phrase X inches to finished grade when talking about how deep to bury conduit refers to the distance from the top of the conduit to the final surface of the ground after everything is built and the landscaping is done. You measure this distance straight up and down from the top of the conduit to where the final ground level will be. So, if you need 12 inches of white rock over the conduit, that means the top of the conduit should be 12 inches below the final ground level. This 12 inches is measured from the top of the conduit to the finished ground surface. Usually, the electrical contractor has to install the conduit and make sure it follows all the rules in the code, including how deep it needs to be buried. But sometimes the final ground level isn't set until after the electrical contractor is done. In that case, a general contractor or project manager needs to work with the electrical contractor to make sure the conduit ends up being buried at the right depth, following the code and the project plans. If the conduit isn't buried deep enough, it's important to fix it so it meets the code and is protected from damage. The National Electrical Code, or NEC, provides specific guidelines for the minimum burial depths of electrical conduits and cables. These requirements are in place to protect the wiring from physical damage, environmental factors, and other potential hazards. The specific burial depth required depends on several factors, including the voltage of the circuit, the type of conduit or cable used, and the location of the installation. For example, direct buried cables typically require a greater burial depth than conduits encased in concrete. In areas subject to vehicular traffic, the burial depth requirements are also typically greater than in areas where there is no vehicular traffic. The NEC specifies different burial depths for different types of wiring methods. Some common examples include firstly for rigid metal conduit, or RMC, and intermediate metal conduit, or IMC. A minimum burial depth of 6 inches is generally required in areas subject to vehicular traffic and 18 inches in other areas. Secondly, for electrical metallic tubing, or IMT, which is typically encased in concrete, a minimum burial depth of 4 inches is generally required. Thirdly, for direct buried cables, such as underground feeder, or UF cable, a minimum burial depth of 24 inches is generally required for circuits up to 600 volts. It is important to consult the NEC for the specific burial depth requirements for your particular installation. In addition to the NEC requirements, local codes and regulations may also impose additional requirements. It is important to check with the local authorities to determine if there are any additional burial depth requirements in your area. When determining the finished grade, it is important to consider all factors that may affect the final elevation of the ground surface. This includes the thickness of any paving materials, such as asphalt or concrete, as well as the depth of any topsoil or landscaping materials. It is also important to consider any potential for erosion or settling of the ground surface over time. To ensure that the conduit is buried at the correct depth, it is recommended to use a level and a measuring tape to accurately measure the distance from the top of the conduit to the finished grade. It is also important to document the burial depth in the project records. If the conduit is not buried at the correct depth, it may be necessary to excavate the area around the conduit and rebury it at the correct depth. This can be a time-consuming and expensive process, so it is important to ensure that the conduit is buried at the correct depth from the outset. In some cases, it may be possible to use a concrete encasement to provide additional protection for the conduit. This can reduce the required burial depth in certain situations. However, it is important to consult the NEC and local codes to determine if this is an acceptable solution for your particular installation. Proper conduit burial depth is essential for ensuring the safety and reliability of electrical systems. By following the NEC requirements and local codes, you can help to protect your wiring from damage and ensure that your electrical system operates safely and efficiently. There are several types of conduits commonly used in electrical installations, each with its own specific properties and applications. Understanding the different types of conduits is essential for selecting the appropriate conduit for a particular installation and ensuring that it meets the required safety standards. Some of the most common types of conduits include firstly, rigid metal conduit, or RMC, is a heavy-duty conduit made of galvanized steel or aluminum. It is the thickest and most durable type of conduit and is typically used in exposed locations where it is subject to physical damage. RNC can be used in both indoor and outdoor applications and is suitable for direct burial. Secondly, intermediate metal conduit, or INC, is a lighter weight version of RNC. It is made of galvanized steel and is typically used in applications where RNC is not required. INC is less expensive than RNC but still provides good protection for wiring. Thirdly, electrical metallic tubing, or EMT, is a thin-walled conduit made of galvanized steel or aluminum. It is the most commonly used type of conduit in residential and commercial buildings. EMT is lightweight and easy to install but is not as strong as RNC or IMC. EMT is typically used in concealed locations and is not suitable for direct burial unless it is encased in concrete. Fourthly, flexible metal conduit, or FMC, is a flexible conduit made of spiral wound metal. It is used in applications where the conduit needs to be bent or flexed, such as when connecting to motors or other equipment. FMC is not as strong as RNC or IMC and is typically used in dry locations. Fifthly, liquid-type flexible metal conduit, or LFMC, is a flexible conduit similar to FMC but with a liquid-tight jacket. It is used in wet locations or where the conduit is exposed to oil, grease, or other liquids. Sixthly, rigid PVC conduit is a rigid conduit made of polyvinyl chloride, or PVC, plastic. It is lightweight, non-corrosive, and easy to install. PVC conduit is typically used in underground applications or in corrosive environments. When selecting a conduit, it is important to consider the following factors. Firstly, the location of the installation. Secondly, the type of wiring being protected. Thirdly, the environmental conditions. And fourthly, the applicable codes and regulations. It is also important to choose a conduit that is compatible with the fittings and accessories being used. Proper conduit installation is essential for ensuring the safety and reliability of electrical systems. The NEC provides detailed requirements for conduit installation, including requirements for support, grounding, and bonding. It is important to follow these requirements carefully to ensure that the conduit system is properly installed and that it provides adequate protection for the wiring. Conduit fittings are used to connect conduit sections, change direction, and provide access to the wiring inside the conduit. There are many different types of conduit fittings available, each designed for a specific purpose. Some of the most common types of conduit fittings include couplings, connectors, elbows, T's, and boxes. Couplings are used to connect two sections of conduit in a straight line. Connectors are used to connect conduit to boxes or other enclosures. Elbows are used to change the direction of conduit runs. T's are used to branch conduit runs in three directions. Boxes are used to provide access to the wiring inside the conduit and to house electrical devices such as switches, receptacles, and splices. When selecting conduit fittings, it is important to choose fittings that are compatible with the type of conduit being used and that are suitable for the intended application. It is also important to ensure that the fittings are properly installed and that they provide a secure and watertight connection. Grounding and bonding are essential for ensuring the safety of electrical systems. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. Bonding connects all metal parts of the electrical system together, which helps to prevent voltage differences and reduce the risk of shock. The NEC provides detailed requirements for grounding and bonding, including requirements for grounding electrodes, grounding conductors, and bonding jumpers. It is important to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. Electrical boxes are enclosures used to protect electrical connections and devices. They are typically made of metal or plastic and are available in a variety of sizes and shapes. Electrical boxes are used to house switches, receptacles, splices, and other electrical devices. The NEC provides detailed requirements for the installation of electrical boxes, including requirements for box fill, support, and grounding. It is important to follow these requirements carefully to ensure that the electrical boxes are properly installed and that they provide adequate protection for the wiring and devices inside. Firstly, box fill refers to the maximum number of conductors, devices, and fittings that can be installed in an electrical box. The NEC specifies the maximum box fill for different sizes and types of electrical boxes. It is important to calculate the box fill before installing any wiring or devices in an electrical box to ensure that the box is not overloaded. Secondly, electrical boxes must be properly supported to prevent them from falling or becoming damaged. The NEC specifies different methods of supporting electrical boxes depending on the type of box and the location of the installation. Thirdly, electrical boxes must be properly grounded to ensure that they are at the same electrical potential as the rest of the electrical system. This helps to protect people from electric shock. The NEC specifies different methods of grounding electrical boxes, depending on the type of box and the wiring method being used. Wiring methods refer to the different ways that electrical conductors can be installed in a building. The NEC recognizes a variety of wiring methods, each with its own specific requirements. Some of the most common wiring methods include firstly conduit, secondly cable, and thirdly open wiring. Conduit is a rigid or flexible tube used to protect electrical conductors. Cable is a group of conductors bundled together in a protective jacket. Open wiring is a method of installing conductors without any protection. The NEC specifies the types of wiring methods that are permitted in different locations and applications. It is important to choose a wiring method that is appropriate for the specific installation and that meets the requirements of the NEC. Overcurrent protection is a critical safety feature of electrical systems. It is designed to protect wiring and equipment from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. The NEC specifies the types and sizes of overcurrent protection devices that are required for different circuits and equipment. It is important to choose the correct overcurrent protection devices for your electrical system and to ensure that they are properly installed and maintained. Ground fault circuit interrupters, or GFCIs, are another important safety feature of electrical systems. They are designed to protect people from electric shock by detecting ground faults and interrupting the flow of current. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. The NEC specifies the requirements for GFCIs, including the locations where they are required and the types of devices that are permitted. Surge protection is designed to protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protection devices, or SPDs, are designed to divert excess voltage away from sensitive equipment, protecting it from damage. The NEC recommends the use of SPD in certain applications, such as in buildings with sensitive electronic equipment. Electrical safety is of paramount importance in all electrical installations. It is essential to follow all applicable codes and regulations and to take all necessary precautions to protect yourself and others from electric shock and other electrical hazards. Some of the most important electrical safety tips include: firstly, always turn off the power before working on any electrical equipment. Secondly, never work on electrical equipment in wet or damp conditions. Thirdly, use properly insulated tools and equipment. Fourthly, never overload circuits. Fifthly, have your electrical system inspected regularly by a qualified electrician. It is important to understand the terminology used in the electrical industry. This will help you to communicate effectively with electricians and other professionals and to understand the requirements of the NEC and other codes and regulations. Some of the most common electrical terms include: firstly, voltage, which is the electrical potential difference between 2 points. Secondly, current, which is the flow of electrical charge. Thirdly, resistance, which is the opposition to the flow of current. Fourthly, power, which is the rate at which electrical energy is used. Fifthly, grounding, which is the connection of an electrical system to the earth. Sixthly, bonding, which is the connection of all metal parts of an electrical system together. Seventh, overcurrent protection, which is the protection of wiring and equipment from damage caused by excessive current flow. It is important to keep up to date on the latest changes to the NEC and other codes and regulations. The electrical industry is constantly evolving, and new technologies and safety standards are being developed all the time. By staying informed about the latest changes, you can ensure that your electrical installations are safe and compliant with all applicable requirements. There are many resources available to help you stay up to date on electrical codes and regulations. These resources include firstly the NEC, which is published by the National Fire Protection Association, or NFPA. Secondly, the International Electrical Code, or IC, which is published by the International Code Council, or IC. Thirdly, trade publications such as Electrical Construction and Maintenance, or EC&M. Fourthly, continuing education courses offered by colleges, universities, and trade schools. By taking advantage of these resources, you can ensure that you have the knowledge and skills necessary to safely and effectively install and maintain electrical systems. When dealing with electrical installations in hazardous locations, such as the liquid hydrogen test facility, it's crucial to adhere to specific regulations and safety standards. Class 1 Division 1 locations, as mentioned, are areas where flammable gases or vapors are present continuously, intermittently, or periodically under normal operating conditions. In such environments, all electrical equipment must be explosion-proof or intrinsically safe to prevent ignition of the flammable substances. Explosion-proof equipment is designed to contain any internal explosion within its enclosure and prevent it from propagating to the surrounding atmosphere. Intrinsically safe equipment, on the other hand, is designed to operate with such low energy that it cannot ignite flammable substances, even under fault conditions. When installing conduit in Class 1 Division 1 locations, it's essential to use threaded rigid metal conduit, or RMC, and explosion-proof fittings. The threads must be properly engaged to ensure a tight seal and prevent the escape of flammable gases or vapors. Conduit seals are also required to prevent the propagation of explosions through the conduit system. These seals are typically installed at the boundaries of hazardous locations and at specific intervals within the conduit run. The NEC provides detailed guidelines for electrical installations in hazardous locations in Article 500. It's crucial to consult this article and follow all applicable requirements to ensure the safety of personnel and equipment. In addition to the NEC, other standards and regulations may apply to electrical installations in hazardous locations, such as those established by the Occupational Safety and Health Administration, or OSHA. It's important to be aware of all applicable requirements and to comply with them diligently. Regular inspections and maintenance are essential for ensuring the continued safety of electrical installations in hazardous locations. Qualified personnel should inspect the equipment regularly to identify any signs of damage or deterioration. Any necessary repairs or replacement should be performed promptly to maintain the integrity of the explosion protection. The finished grade plays a crucial role in ensuring the proper functioning and safety of electrical installations. It provides a stable and level surface for equipment and structures, and it helps to prevent water damage and other environmental hazards. The finished grade should be carefully planned and constructed to meet the specific requirements of the electrical installation. It should be sloped away from buildings and equipment to promote drainage and prevent water from accumulating around foundations. The surface should be compacted and stabilized to prevent settling and erosion. The finished grade should also be protected from damage caused by vehicles, equipment, and other activities. Barriers and other protective measures may be necessary to prevent damage to underground conduits and other electrical infrastructure. Proper coordination between the electrical contractor, the general contractor, and other trades is essential for ensuring that the finished grade is compatible with the electrical installation. The electrical contractor should provide input on the required elevations and clearances, and the general contractor should ensure that the finished grade is constructed accordingly. Regular monitoring and maintenance of the finished grade are necessary to ensure that it continues to meet the requirements of the electrical installation. Any settling, erosion, or other damage should be repaired promptly to prevent problems from developing. Proper documentation of the finished grade is also important. As-built drawings and other records should be maintained to show the final elevations and locations of all electrical equipment and infrastructure. This documentation can be valuable for future maintenance and repairs. When planning an electrical installation, it's crucial to consider the long-term effects of the environment on the equipment and materials. Factors such as temperature, humidity, sunlight, and chemical exposure can all affect the performance and lifespan of electrical components. It's important to select equipment and materials that are suitable for the specific environmental conditions at the installation site. For example, in areas with high humidity, it's important to use corrosion-resistant conduits and enclosures. In areas with extreme temperatures, it's important to use equipment that is rated for the appropriate temperature range. Sunlight can also degrade certain materials, so it's important to protect electrical components from direct sunlight exposure. Chemical exposure can also be a significant concern in some environments. It's important to select materials that are resistant to the specific chemicals that are present at the installation site. Regular inspections and maintenance are essential for identifying and addressing any environmental damage to electrical equipment. Any corroded, cracked, or otherwise damaged component should be replaced promptly to prevent safety hazards and equipment failures. In addition to selecting appropriate equipment and materials, it's also important to take steps to mitigate the effects of the environment on electrical installations. This can include providing shading, ventilation, and drainage to protect equipment from the elements. It can also include applying protective coatings and sealants to prevent corrosion and other forms of environmental damage. By carefully considering the environmental factors and taking appropriate precautions, it's possible to ensure the long-term reliability and safety of electrical installations.